today we are going to talk about different techniques for solving some more complicated trigonometric equations. We're going to use something called trig identities. An identity is basically just a true statement involving trig identities in this case. So let's take one of the most basic trig excuse me, one of the most basic trig identities there. Sorry if it's a little quiet. I forgot to slide my microphone down to my mouthpiece there. Let's take a peek at our unit circle. As you notice, everything comes back to our unit circle. And remember, the size of the circle is really not that important. The fact that these are all similar triangles. If I come out here at pi over 6 radians, even if the circle is too long, right, if it's double for the radius here, the coordinate out here will be twice as big, but we're defining things to be x over r, so if it's twice as big and you're dividing by something twice as big, it'll come down to the same value. So that's why we always reference the unit circle. So root 3 over 2. Root 3 over 2, that's the x-coordinate. That means this distance right here, the horizontal distance, is the square root of 3 over 2, and that's straight down there. And this is the y-coordinate. The vertical distance is 1/2. Well, that is true about every coordinate on here. If I take root 2 over 2 and root 2 over 2, right, and I can drop another triangle down and label that the same way. Well, hopefully what you recognize about all of these triangles, and it doesn't matter if it's a major coordinate or not a major coordinate, right, if I take 1/2 and root 3 over 2, I can do the same thing. This is root 3 over 2, that's 1/2, and the radius is always 1. These are all right triangles, and what is the one thing that we know about every right triangle? Yep, I think I heard somebody say it. A squared plus B squared equals C squared. A and B are legs, right? These guys are the legs. And this is the hypotenuse. The hypotenuse of our triangle, which is inside of a circle, is actually our radius. And our legs are actually our cosine and sine values. So for our purposes, the Pythagorean theorem looks like sine squared of some angle plus cosine squared of that same angle equals the radius squared, which is 1, right? So root 3 over 2 squared. Let's see if that holds true. Root 3 over 2 squared. And keep in mind, root 3 over 2 is nothing more than the cosine of pi over 6 squared plus 1/2 squared. Well, 1/2, remember, is nothing more than the sine of pi over 6 squared equals 1. And remember, the 1 is nothing more than the radius squared. So square root of 3 squared is 3, 2 squared is 4, so we have 3/4. Plus 1 squared is 1, 2 squared is 4, so 1/4. And that certainly equals 1. Pythagorean theorem holds true here. Is identity number 1. Sine squared plus cosine squared equals 1. And this identity, we're going to build other identities off them. So this is the one you want to memorize. And you really know it already. A squared plus B squared equals C squared. X squared plus Y squared equals R squared. Equation of a circle. Okay? Here I'll write X squared plus Y squared equals R squared, the equation of a circle there. This is the equation of the unit circle. All right, so let's put that in perspective a little bit here. I want to go to a clean sheet here. We have sine squared plus cosine squared equals 1. Now I know I don't say the theta, but make sure you always write theta. Sine squared of an angle plus cosine squared of the same angle equals 1. Well, from this, clearly I can get cosine squared equals 1 minus sine squared. Subtract sine squared from both sides, right? Or I could say that sine squared equals 1 minus cosine squared. Also true, right? All subsets of that. Likewise, or similarly, if I divide everything by sine squared, divide by sine squared. I get 1 plus cosine squared divided by sine squared, which is cotangent squared, equals 1 divided by sine squared, which is cosecant squared. And from there, cotangent squared equals cosecant squared minus 1. Or, not as helpful, but you could say 1 equals cosecant squared minus cotangent squared. Not really that helpful though, so I'm not going to write that. Well, if I divide it by sine squared, it stands to reason that I will also divide by cosine squared. Sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1, and 1 over cosine squared is secant squared. And likewise, I can say that tangent squared is equal to secant squared minus 1. Okay, these are the three big guys here. This is the biggest. Sine squared plus cosine squared equals 1. Everything comes from there. These other two are the remaining two Pythagorean identities. Okay, they are Pythagorean identities. They're the big guys. Everything comes from this guy. He is the big guy. These guys are just other big guys. All right, and of course, these are just manipulations of the equation, if you will. A couple other things to talk about, some that should hopefully kind of be logical. The sine of theta, right? Let's think about this in our heads here. Sine of theta, if I take an angle right here, let's make it easy, 45 degrees. My sine is positive root 2 over 2. Well, here at negative 45 degrees, I get the opposite. I get negative root 2 over 2, right? So comma, let's do root 2 over 2. We're just looking at the y-coordinate, and down here I'm at negative root 2 over 2. So the sine of 45 gives me positive root 2 over 2. The sine of negative 45 gives me negative root 2 over 2. So the sine of negative theta, I think is how I want to write this one. I'm trying to think how I want to write this. Let's leave it like this. The sine of theta equals the opposite, the sine of negative theta. Or you could say negative sine of theta equals sine of negative theta. This might be the clearer way right here. Probably the better way to look at it. Similarly, the cosine of theta, so now let's look up here, cosine of 45 degrees is root 3 over 2, and the cosine of negative 45 degrees is still root 3 over 2. So cosine of theta is the same as cosine of negative theta. Okay, the cofunction identities there for cosine are exactly the same. And you can do a bunch of similar things with the relationships with negatives. I think I mentioned cofunctions there by accident. That's the thing I want to do next. So let me just jot out the other ones. So sine of a negative angle is the opposite of sine. Cosine of theta is equal to the cosine of negative theta. You can do your cosecant of negative theta is equal to negative cosecant of theta. You can do tangent of negative theta is equal to negative tangent of theta. And then you have the ones that match up the cosine here. Your secant of negative theta is the same as secant of theta. Missed my parentheses here. And cotangent of negative theta is the same as cotangent of theta. So the guys that are the same are the ones that relate to cosine, right? Cosine, 1 over cosine, and cosine over sine. The ones that are opposites are the ones that relate to sine. Sine, 1 over sine, and sine over cosine. Okay, so those are the opposite there. Relationships with negatives, we've talked about the Pythagorean relationships. You guys already know the reciprocal relationships, right? Sine, or 1 over sine is cosecant, 1 over cosine is secant, 1 over tangent is cotangent, that stuff. The last piece here is our cofunction relationships. Cofunction relationships. And this board's not working so hot right now. At any rate, you guys all mentioned when we were graphing it that the sine and cosine curves look the same, but they were just a shift of each other. And you mentioned a shift of pi over 2 or 90 degrees. Well, that's exactly correct. The sine is the same thing as the cosine of 90 minus theta. Or pi over 2 minus theta, right? Same thing. It's just nicer to write 90 minus theta. And likewise, the cosine is the same as the sine of 90 minus theta. Tangent is the same as, notice cofunction relationship, cotangent of 90 minus theta. Likewise, cotangent is the same as tangent of 90 minus theta. And of course, we can do the same for the secants and the cosecants. See if this page scrolls down here. There we go. Secant is the same as cosecant of 90 minus theta, and cosecant is the same as secant of 90 minus theta. All right, and we will use these identities here in the near future. Lots of practice problems and stuff. Basically what this is saying is that the sine of 50 degrees, oh, lost some stuff here. Let me start that over and bring these guys back. The sine of 50 degrees is the same thing as cosine of 90 minus 50. In other words, the sine of 50 is the same as cosine of 40. And that should be evident from our unit circle here as well. And I'm just looking at some of the work here we did. I used different angles here, 45 degrees and 30 for, so this stuff looks weird. Ignore those coordinates. In fact, we're just going to get rid of them right now. We'll leave the y's up there because I was talking about 45 degrees at that time. If we think about 30 degrees or pi over 6, right, my x is root 3 over 2, my y is 1/2, or my cosine is root 3 over 2, my sine is 1/2. 30 degrees, 90 minus 30 is 60. Well, this says that the sine of 30 should be the cosine of 60. The sine of 30, sure enough, is the cosine of 60. Okay, and that's why our coordinates flip-flop here. xy, yx, because 90 minus 30 is 60. These guys are proving the cofunction identity, or at least are showing that it works in that scenario. All right, so those are our Pythagorean identities. Again, we'll get into using them to solve equations a little bit here in the near future. Have a good one.